Welcome to the 23rd lecture video for Physics 4C. We are wrapping up our coverage of fully quantum mechanical treatment, roughly matching up to what is covered in Chapter 7 of OpenStax University Physics, Volume 3. As our second and last example of fully working out the wave function solutions to the Schrödinger equation, we work out the reflection and transmission coefficients for a particle wave incident on a step potential. We start with example 1, in which the total energy of the incident wave is higher than the potential energy step size, which results in a good, but not 100%, transmission of the incident wave. After we have worked out example 1, and have some confidence in applying the boundary conditions to the general wave function solutions to the time-independent Schrödinger equation, we solve example 2, in which now the particle energy is lower than the step potential energy. While your textbook derives the tunneling probability for a finite potential wall, we are not going to do that ourselves, because adding the second step introduces a lot of calculational complexity. For the purposes of the homework problems, you can look up the tunneling probability formula derived in the textbook. What we are going to do is use computerized tools to help us develop intuition and work through these more complicated scenarios. We will first look at the behaviors of wave packets incident on a step potential using the PhET simulation, developing some physical intuition for this situation. Then, for the last lecture video here, we are going to work through the tunneling and reflection probability, but with the help of the SageMath computer algebra system. Again, this is our last lecture video in the series covering Chapter 7. In the next set of lectures, we will look at Chapter 8, Introducing Atomic Physics.
And this set is actually missing one set of topics that's covered in Chapter 7. And that's what we are covering at the beginning of class today, solving Schrödinger equation with a step potential. Your textbook tries to cover it all in one section, quantum tunneling. And what we are going to do is we are going to break it down into steps and do a portion of it. And I'll just highlight the application to quantum tunneling, but we won't actually do it. I learned from last time I taught this class that there's not enough class time to actually do it in class. But I will write an additional assignment that's going to be due next Tuesday. It will be tutorial for that type of calculation, because I think that's one detailed quantum calculation you can do that's not infinite square well. The rest are a little bit too mathematically sophisticated for this class. All right, so let me get started. So we are wrapping up Chapter 7. So even though I didn't put this here, we are wrapping up Chapter 7. Let me just remind you of what we were talking about last week, or last few weeks, but especially last week. So this is the time-independent Schrödinger equation. And so for the, let me write it down first. Time-independent Schrödinger equation, minus h bar squared over 2m, second position derivative. And when I write down the time-independent Schrödinger equation, I don't write this as partial derivatives anymore, mainly because the function that you are taking derivatives of should only be a function of x. It should no longer be a function of position and time. Plus the potential term is equal to energy times the wave function. And I'm hoping by now you kind of remember the key difference between the time-independent Schrödinger equation and time-dependent Schrödinger equation, which we actually started out with. And the key difference, if you kind of want to note it for conceptual purposes, is really on the right-hand side. The time-dependent Schrödinger equation was written out as I h bar partial time derivative of the time-dependent wave function. And really, this here is the energy operator. This is the mathematical device that's measuring energy of this wave function. So conceptually, when you go from time-dependent Schrödinger equation to time-independent Schrödinger equation, you are making an assumption that whatever state you are dealing with is at a very particular energy. It's in an energy eigenstate. It's one of those stationary states. Oh, I guess that's actually covered in the reading assignment due tonight. Oh, how are stationary states stationary? That's one of the senses in which it's stationary. So these energy eigenstates are the I guess simplest wave function state to deal with. So that's what we'll be dealing with most of the time. So with the step potential that we are going to talk about, I guess when you are visualizing it, it's easy to visualize it as a kind of traveling wave solution particle. But we are going to write down the time-independent version. Sort of, this is the energy eigenstate, and we are sort of choosing to look at stationary picture, like what you would have after a stream of particle has come for a long time, and then, what do you see? Good. Okay, so we've been dealing with this Schrödinger equation actually for some time now. We've, I think, used this for infinite square well, right? So as a reminder, for infinite square well, this is how it got applied to. So you have, this is the infinite square well. The potential goes to infinity at either end, and potential is 0 here. So for this infinite square well, the Schrödinger equation became really simple because outside here, wave function has to be 0. Otherwise, this term goes to infinity, and we don't really want to deal with infinities. So when you look at all the wave function solutions, they all have to come to 0 at the end, no matter what happens in between. And in between, potential is 0. So the Schrödinger equation becomes pretty simple. It simply becomes the kinetic energy term, minus h bar squared over 2m, double position derivative of wave function is the energy wave function. And we get an oscillatory solution. You get sines and cosines with these matching boundary conditions that at the end, the wave function has to be 0. Like, that ring a bell? That's the only detailed calculation we have done so far. And I guess for a while, I thought maybe we will try doing this with a finite well, but I think that comes into the same problem. The finite well calculation is actually mathematically involved, and it's kind of numerical. It has to be all numerical in the end. So I don't think it's any kind of question I can give you on the final exam or exams anyway. So we'll skip finite square well also. You can read about it. We might do some simulations on homework, but so this is the only context where we have actually solved the Schrödinger equation so far. And I'm giving you one additional context where you can actually solve Schrödinger equation. The mathematical tools we have, the mathematical training you have are enough to actually solve Schrödinger equation in this circumstance. And these are, so once again, I'm essentially taking what your textbook covers in this section, chapter 7, section 6, and they kind of go through this quickly because they are putting in what ought to be in a several modules into a single section. But let me just put it on a particular place so that you have some idea of where we are heading to. So here they are working out the case for where you have two steps actually, a step up and then a step down. And then when they talk about tunneling, it's the idea that particle here, which has some energy, which is not high enough to classically go over this barrier, actually ends up getting transmitted on this side. You saw this on the simulation lab, and in this section, they actually go through the calculation and do all that. So that's where we are heading to. But in the interest of time, what I'm essentially going to cover in class is this portion here. just the first step. And we won't do the second step because I feel like there's not enough time to do everything there. But we'll actually look at the two different cases. We'll look at the case where incoming energy is less than the step size, and we'll look at when the incoming energy is more than the step size. So it'll have more variety that way. So that's one other situation where we can actually solve this Schrödinger equation. And you can kind of see why. Let's see. So Schrödinger equation with step potential, meaning when you look at this potential energy function, it's a piecewise linear function. In fact, it's a piecewise linear horizontal line function. So here's one kind of simplest step. It can be 0 for all values of x below some particular value. Let's make things easy for ourselves, and let's say for x less than or equal to 0. And when x becomes greater than 0, then the potential energy changes discontinuously, and it becomes some constant value V naught. And this is a situation where we can actually solve a Schrödinger equation exactly. We have enough tools in our arsenal to actually go through that. And this is really the reason why. Let me rewrite this so that I have this potential with the energy term. I'm just going to move this over to the right-hand side. Then this is what Schrödinger equation becomes. Minus h bar squared over 2m, second position derivative of wave function is equal to. So I guess let me write down three different forms here. The first would be the most general form. So I'm imagining moving this over and factoring out the wave function. So E minus V of x psi x. Now, this one is a difficult equation to solve. In fact, if you have taken differential equations, you kind of know that without knowing the exact form of this function v, there's no general solution. You need to know what this function v as a function of x is, right? How many of you here taken differential equations are taking? Like you've seen that, right? Yeah, so this case we don't do because there's no general analytical solution. Now, if my potential is 0, then that's a situation where we have already solved before. It's simply E psi x, and we've done that before. We know how to do it. I guess you get oscillatory solution, and you're almost done. Even in the second case, it's still doable because all you have is this constant value E will now have become E minus V naught. So instead of dealing with one constant value, you're simply dealing with a slightly different constant value. So at least in general idea, because this is constant, this is essentially the same equation as this, with one possibly key difference. Before I mention anything, can anyone see what one possible key difference between these two might be?
The symbol, it can be negative or positive.
The sign, yeah. The energy, if you're dealing with a free particle, energy kind of has to be positive. Like negative kinetic energy makes no sense. Like, I don't know what even that means. So you have positive energy, and you can have positive potential, which means now here, there's a possibility of this constant being negative. And somehow you have to be able to find a wave function, which makes physical sense with that in mind. So that's really the only thing new here. Your constant here might be negative instead of positive, and you'll have a different class of solutions that matches that. So this is the step potential. Let's just work through one. I think rather than me babbling on, well, I guess I'm still babbling, but it's a lot easier when I know what I'm babbling about. So let me just go through an example. So let's say, let's call this example 1. Example 1. And let me do the most, I guess, simplest example. It's step up potential where energy is greater than V0. I feel like this would possibly be the most boring example. Because what we would be describing then is where I have, let's say this is still my potential step, but the particle that's coming in would have enough energy here. This would be the energy that the particle has in that case. So classically, you wouldn't expect anything to happen. It's like your textbook talks about ball rolling. The rolling ball has enough energy to climb up this hill. So it does, and it keeps on rolling. That's the boring classical version of it. I'm actually oversimplifying, but even in the quantum mechanical case, this is mathematically least complicated. So let's go through it so that we can see what's involved in working through something like this. So, so that I need a drawing to help me think through. So let me have a drawing of potential. So this is the line for potential equal to 0. There's a step up somewhere. And I'm just going to define my coordinate system so that this is x equals 0. You will soon see that this actually does make my life a little bit easier. More so than if this wasn't 0. And so this is my potential size, V0. And I'm just going to have a representation of energy of the particle. Let me just draw that line here. This is the energy of the particle. Yeah. And later on, I'll sketch something onto this to represent the wave function of the particle with this being the 0 line. That's kind of common convention to draw things. So, so this is our goal. We want to solve this Schrödinger equation for this potential, which can be expressed in this way, which means what I'm trying to do is I'm trying to find the mathematical formula for psi that I can plug it into here with these values of potential here and see that left-hand side equals right-hand side. That's what solving differential equation means, right? So let me ask you this question. Would I be able to find an analytical algebraic form, analytical form of wave function that works for all the regions, or from negative x to positive x? Like, could I, if I don't know, let's say I did my usual guess thing. If I guessed, let me do it in different color. If I guessed psi of x, I don't know, my usual guess exponential, a e to the I kx, then if I guessed this as my solution and then plugged it in, could this possibly work for all values of x? So there's a barrier here. It's really that you are actually dealing with two equations. You have one equation that works for x less than 0, where potential is, potential is 0. And you have a second equation, same left-hand side, but now different right-hand side, that works for x greater than 0. So once you recognize that you actually, rather than thinking of this as one equation, because your potential is piecewise defined, your equation is also piecewise. So that probably means your solution also has to be piecewise. So this is a good starting place. The recognition that you kind of have to break up this problem. So what you have to start out with is when I work out solution for my wave function, I'm not going to have one solution, one form that works for everything. It's really going to be divided piecewise into some value of x less than 0. That's going to be one region. And for value of x greater than 0, that's going to be for another region. So I'm going to have some wave function 1. Oops, that's not the way to label it. So let me label the regions. So x equals 0 is the natural dividing line. So I'm going to have something that works for region 1, and I'm going to have something that works for region 2. So for region 1, I'm going to have some kind of solution for region 1 as a function of x. And for region 2, I'm going to have a second expression that works for region 2. So does this approach make sense? I'm hoping, even if you didn't guess this is how we might do it initially, that this makes sense. Good? Yeah?
Are you going to make sure that they
yeah.
get smooth?
So we have to make sure that the solution here matches with, it flows smoothly with the solution here. And so this is what it means. I'm glad that Javier brought this point up. Imagine that somehow you end up having this as the solution, like some kind of oscillatory thing here. And then suddenly here, your solution starts out something like this. Then this is going to be problematic if you have this discontinuity in wave function that's unphysical, and you don't want to do that. So we have to enforce something called boundary conditions. And this is something you might have seen in your differential equations class, right? Or sometimes they call it initial condition because your boundary happens to be kind of initial time or initial whatever. In this context, we call it boundary condition. It's condition at the boundary. And I guess now is the time. Oh, I promised last time that I would give you the rules for the boundary condition. So let me do that now. And this time, I can actually justify these rules. One of the rules you have heard already. The first two of the boundary conditions is the continuity of the wave function. That I guess you can put it this way. Psi 1 at x equals 0, that's the wave function on the left-hand side, right at this, has to be equal to the value of the wave function right on the right side of the boundary. We've been actually using this condition from the very beginning. When we were talking about infinite square well, we kind of enforced it here without justifying why that must be. But let me come back to that in a bit. I'll give you the second boundary condition that's easier to explain without imagining doing this integral. So the second boundary condition actually looks a lot like this. Second boundary condition is continuity of not the wave function, but the first derivative of the wave function. Sometimes people call this smoothness of the curve. Because when the first derivative is discontinuous, you are going to get a little kink where the slope suddenly changes. This means slope cannot change suddenly. Or writing it out, it'll be derivative psi 1 with respect to dx at x equals 0 is equal to derivative of psi 2 with respect to x at x equals 0. Good? And this is actually a lot easier to explain simply using Schrödinger equation here. So I can just use the Schrödinger equation. If your derivative is discontinuous, then what can you say about the second derivative?
It's infinity.
That it approaches infinity. That's what we were just talking about. That means this term is going to approach negative infinity, which means the only way you could have discontinuous first derivative is only if some of these are somehow infinite. In fact, this is the example where you had a discontinuous derivative, and that was possible because I had the infinite potential. That was the only loophole that's there. But with the step potential, all my potentials are finite, so I don't have that loophole anymore. So this boundary condition now applies. Yep. So that's the second boundary condition, but easier to explain here. So so this is kind of I guess this is a weaker boundary condition than this, in that there are loopholes to this. If your potential goes to infinity, then you can violate this, as you have seen here. Yep. Now let's go back to the first boundary condition. Sorry, this is not the rigor. Sorry, let me just hand wave it this way. You know this is correct, right? So right now I'm not quite coming up with the correct rigorous justification why this is correct, but this is one distinction between physicists and mathematicians. As long as we know it's correct, we don't need to be able to prove that it's correct. So we'll just use it, yeah?
Can we do one more integral, like to the double
Yeah,
integral?
I'm a little bit uncomfortable doing that, because when I do that, I've plugged in actual constant value, so it's no longer a function. So as long as if I'm trying to do something like concretely, I want to do it actually rigorously. So yeah, so I'll just leave it here. You know this is correct. I haven't proven it, but you know this is correct. Like, it doesn't make sense any other way. I'll figure it out later what I messed up. So that's what we are going to do. Let me just lay out the solution step. So the solution step is this. First, so you have a fairly simple differential equation. So the very first solution step is find general solutions to Schrödinger equation. And that'll be pretty quick. You kind of know what the answers are already. And then general solution to Schrödinger equation for all regions separately. Then what you are going to end up is you are going to end up with some number of equations and a number of free parameters. And the rest of the goal in solution step is to reduce the number of free parameters by applying boundary conditions. So second step is reduce free parameters. That's in the general solution by applying boundary condition. Or in your differential equations class, they would call this finding or find specific solution. Is that the term? Particular. Find the particular solutions for the initial condition, or in our case, the boundary condition. So let me go through that step for this. This is, as I said, the easiest case, so it doesn't take that long. So let me just do that. So for region 1, the Schrödinger equation we are trying to solve is this one. Let me rewrite it in a format where you can kind of guess the answer pretty easily. So I'm going to solve it for the second derivative. Then I have, for the Schrödinger equation, second position derivative is equal to, move all the constants over, minus 2me over h bar squared psi x. Have you seen something like this before? Yeah, where have you seen it?
Simple harmonic oscillator.
Yeah, simple harmonic oscillator. Two derivatives, get the same function back, and you have negative coefficient in front. Right? Now, so it's easy for you to say, oh, then my solution is psi of x is, in general, a cosine of kx plus b sine of kx, where k is defined as square root of 2me over h bar squared. It's easy for you to say that. Let me write down the different version, because the problem with this version is that neither of this cosine and sine have a very clear, physically assignable meaning. So it kind of gets mixed up. So I want to use the complex exponential version, because with the complex exponential version, there is a clear physical meaning we can assign to, and that will help us reduce number of free parameters. So instead of this, I'm going to say this. Psi of x is still two coefficients. Coefficient A times e to the I kx plus coefficient B times e to the minus I kx. Where k is still defined the same way. Square root of 2me, and I pulled out h bar so that now it's just divided by h bar. Good? And you can see how by combining these coefficients differently, you can get cosine, you can get sine, right? So they will cover the same space of functions. All right, so that's so that's the general solution for psi 1, the wave function in region 1, and this is really should be k1. Let me just start using different symbols so that I'm tracking them correctly. Let me do that for region 2. Region 2 will be not that much different. So for region 2, as I said, this is the simplest case. It's because it's kind of boring. So I get this. The second position derivative wave function is equal to minus. And let me write out all the coefficients here. Minus 2m e minus v naught over h bar squared psi of x. Has anything here really changed from here? Yeah, not really, right? E minus v naught is still positive, which means this coefficient is still negative overall. So you still get oscillatory solution. So that's what I mean. This is the boring case. It's one same solution just over and over again. So it's psi 2x is, well, it could be different coefficients. So let's do c e to the I, this time k2x plus d e to the minus I k2x, where k2 is square root of 2n e minus v naught over h bar. Good? Yeah. It seems so boring until you start counting the number of unknowns and trying to reduce the free parameters. So some of the things got determined right out of the gate. These k parameters, they are defined in terms of the energies and potentials, so that's all known. These are your unknowns, A, B, C, D, which means potentially we have to find 4 equations to determine all those. Let's just, in this step 2, let's just try to count the number of equations we can write down. I think I can write down one equation, this, right? I plug in x equals 0 to here and here, say that they are equal to each other. In fact, let me write it down. I kind of need it eventually anyway. So let me write down. So I have one equation. When I plug in x equals 0, this becomes 1. Plug in x equals 0, this becomes 1. This is why I kind of wanted the boundary to be at x equals 0. It makes my life easy. So it becomes, all right, a plus b is equal to c plus d. All right, that's 1 so far. I need 3 more. Where can I find my other equations? Are there more boundary conditions to apply? Yeah, there's one left. I can try this. Yeah. And so that means I have to take the derivative, plug in x equals 0, and then set them equal to each other that way. So in fact, because these are exponentials, the derivatives are kind of easy. Each time you take the derivative, I just get a factor of ik coming down. And when I plug in x equals 0, this will be 1 again. So the second equation, I can kind of do it in my head and write it down this way. Just double check me and see if I did everything correct. Second equation will be ik1 times a times 1. And it'll be minus ik1. So it'll be minus ik1 b is equal to, that's the left-hand side, and the right-hand side is the derivative of this. So ikc minus, 2, ik2d. Everything looks correct there? Okay, yeah, but that was actually simple enough calculation, which is why we can do it. I still need 2 more equations. Yeah, so what it will come down to is that this is an underspecified problem. If I simply said, here's a step, find me solutions that fit the step, I haven't specified enough. I have to give you a very particular physical situation to be able to expect some concrete answer out of that. It's different from this bound state infinite square well, in that I cannot simply say, if we have a step and put a particle near it, it could just go infinitely far away. That could be your solution, and it's a very uninteresting solution. So what I would instead do is, let me specify this situation. I'm going to say I have this step, and I actually have a particle that's moving towards the step. Meaning I have an incident wave that's coming from left to right. That actually allows me to reduce this down to a single Fourier parameter, because one of these 2 states represent a solution state that's traveling to the right, and one of these 2 states represent a solution state traveling to the left. Any guesses which is which? Which way does this, do you guess this one travels? To the right, and this one you guess travels to the left? Yeah, that would be the correct guess. And wait, yeah, that is the correct guess. And the way to double check it is using the momentum operator. Remember, this is the momentum operator, minus I h bar derivative with respect to x. So if you apply the momentum operator and you get positive momentum, that means it's moving to the right. If you get negative momentum, that means it's moving to the left. Okay? So by focusing on that very particular situation, we can say, all right, my incoming particle is, okay, I have to be careful here. My incoming particle is moving from left, and I think that does not mean I can eliminate B, because this just reminded me, there could be a reflected wave that's coming back. So I have to leave this B alone, but what I can get rid of is this D. Because after the barrier, the only thing that's after the barrier is what got through. There's nothing that's coming from the right to the left. So I can get rid of this. So I can get rid of D here. I can get rid of this D here. All right. I still need one more way to reduce the number of free parameters. So this is, I guess, a question of what you want to find out. So this is the question you can ask. So you are looking at so think of this like a light incident on some transparent surface, like, I don't know, I don't have anything transparent. But if this is glass, you've seen it how some light reflects, some light is transmitted. And in that case, if I'm wanting to find out the property of this barrier, really what I want to know is, what is the reflectivity? What is the transmittivity? How much of the incident wave goes through? How much of the incident wave reflects? So here, instead of trying to find out the exact number of the particles that go through, or probably there's something getting through, you can try to find the ratio. Essentially, what you would be limiting yourself to is trying to figure out, what is the ratio of C over A, which would be related to how much particle is transmitted, and the ratio B over A, which would be related to how much particle is reflected. So in other words, instead of So I guess you can, here's maybe one way to kind of mathematically represent that. One way to mathematically represent that would be to say I'm going to say my A is equal to 1. Okay? And then whatever value of B and C I get is that what this ratio would be if I didn't say that my A is equal to 1. Okay? So I can say, all right, this A, let me just set that equal to 1. And this A, let me just set that equal to 1. Okay? Then now I have two equations, two unknowns, B and C. Now I can solve for it. So let me solve for it and just to show you some physical meaning of the result you get. Because I think it's actually an interesting result that you should see that agrees with your intuition. So, all right, let me just rewrite this. I made a lot of modifications here. So 1 plus B is equal to C. That's what that says. 1 plus B is equal to C. I can actually cancel out I. It's in every single term. So let me cancel out I. Then what this says is Ki times 1, so minus Kib is equal to K2C. All right, I guess it's just a simple algebra to go through. Let me try to reduce the number of steps because I'm kind of running out of space here. So what I'm going to do is I'm going to multiply this through by Ki, or at least I'm imagining that I do that. Because once I do that, I can do linear combination. When I add these two together, I'll get rid of B, right? So by doing linear combination, adding them together, what I end up with is Ki plus Ki. So 2Ki is equal to Ki plus K2. So Ki plus K2 C. And I can solve for C as, so C is equal to 2Ki over, or 2K1 divided by K1 plus K2. And let me just, from these two expressions, remind you that K1 is always greater than K2. Because K2 is where you take the number, subtract something, so it's always a smaller number. So, all right, so this is one result. That's the coefficient C. And to get B, you would subtract them. So wait, you do subtract? No, sorry, you don't subtract that. All right, it's a little bit longer. I think it's actually simpler to do it this way. What's the simplest? Here, simplest thing to do is to plug this in for C here and solve for B here. So doing that, I get B is equal to C minus 1. So that minus 1 to Ki over Ki plus K2 minus 1. Or turning this minus 1 into a more interesting fraction of K1 plus K2 over K1 plus K2. And when you do the subtraction, one of this cancels out one of that. And I have minus K2. So you end up with this whole thing is equal to K1 minus K2 divided by K1 plus K2. So this is the coefficient B. Good? Any questions? there are some, I guess that's correct. I was trying to see if I can intuitively guess what the result should be. You know, so I'm trying to think, okay, what's an interesting energy level to look at? While E is still greater than V naught. Well, I guess an interesting energy level to look at is right here, where E is barely greater than V naught. So in that case, I can say K2 goes to 0, and K1 is just some value. And what I was kind of hoping to be able to say is that transmission probability is 0. But I don't think that's the case. At least if I did this right. Oh, I think I know. I've made this mistake in the past. I know what I'm getting off to. It has to do with calculating the actual probability. Let's see. I don't want to get too deep into that. So let me look at the other limit. The other limit is easier. So we have some reflected probability, right? And when you look at this answer, there's at least one thing you can kind of infer from that. So, you know, simple thing to infer, the larger the B is, the greater the probability that particle will be reflected, right? So looking at this number here, so if the energy is much greater than V naught, then these two numbers are going to become very similar to each other. So in the limit that energy goes in the limit that energy goes to infinity, this number will go to 0. So we can say that if your incoming energy is much larger than the step size, then the probability of something being reflected is 0. Or it approaches 0, which is what you would expect classically or whatever. Okay? The other thing that's, so that's something that matches your intuition, at least says that this result is not completely out of touch with the reality. The other thing that's interesting is in the simpler limit where, I don't know, if your E is equal to 2V naught, then this is definitely not 0. Where you have some step size, and if your incoming energy is double the step size, even though you have plenty of energy coming in, you have some non-zero probability of things being reflected. In fact, here's how you can calculate reflection probability. So these are coefficients, and what I hope you kind of remember from what we were covering with the quantum mechanics before is psi. It gives you the wave function amplitude, right? And this word amplitude, it has no physical meaning. It doesn't correspond to anything you can measure physically. What does have physical meaning is the psi absolute value squared. That corresponds to probability density. And it corresponds to, in the case of traveling particles, it corresponds to intensity. How much energy is coming in. So here, if you want to calculate reflectivity or reflectance, the ratio of the incoming number of particles and the reflected number of particles, what you really need to calculate is B absolute value squared. So what you need to calculate is B absolute value squared, and that gives you this result. So taking this, squaring both sides, you end up with ki minus k2. I don't know. I guess it's just doesn't do anything interesting. Ki plus k2 squared. I guess that gives you the reflectivity. Before we go into break, let me just leave with this comment. Does everyone here have intuition that number of reflected particles and the number of transmitted particles should add up to the total number incident, right? So what that intuition will maybe lead you into saying is b squared plus c squared is equal to 1. And I will tell you right now, if you try to check that with this, you will see that they don't equal 1 when you square them and add them. So that's the question mark. Are they really equal to 1? They are not. And the little part that takes a little bit too much time for us to work through, so I'm not going to do that. The part that you have to account for is the velocity. How quickly are the particles moving? So for B, it's actually simple because the incident and outgoing, they are moving at the same speed. So any factor relating to velocity cancels out. But the outgoing side is where your velocity changes because you've taken up some potential energy. Now you have less kinetic energy. That means smaller velocity. So this is something you never had to deal with light. But now you have to deal with for matter waves. So there's a missing factor here, which I don't know, missing factor. Factor for change in velocity, which takes too much work to work it out, at least for the purpose of this class, so we won't. It actually doesn't take that much work, but we are trying to cover a lot in a short amount of time, so we'll skip that. Welcome back. So we are still working through the step potential, same procedure. Now what will be different is instead of considering case where energy is greater than the potential, we'll be looking at where maybe my energy is now less than the potential. Okay? Otherwise, much of it remains the same. So I'm still going to start out with, well, my wave function is going to be divided into two regions. I'm going to find my general solution. I'll find my general solution. And then I will reduce the number of free parameters by applying the boundary condition. And it's still going to be the same boundary condition. So I guess that means in region 1, nothing changes, right? It's the same differential equation, same general solution. So I guess I should write down again what the definition of K1 was. So the left-hand side, nothing changes. K1 is still square root of 2m e over h bar. And as far as the general solution goes, this is still the form. And like before, I'm still going to say later A is equal to 1 to look at reflectivity and just the reflectivity. Transmittivity is a little too hard now. All right, so that's fine. Now, it's in the region 2 where things change a little bit. So let me make changes as we go. What's the sign of E minus V naught for this condition here? Now it's a negative. So the form of this is a little bit deceptive because this coefficient as a whole is actually positive now. So let me rewrite it so that I don't have this mistaken perception that I'm somehow dealing with negative coefficient. I'm dealing with a now positive coefficient. So if this coefficient is positive, would I still have a harmonic oscillator solutions? No, right? Sines and cosines, when you take two derivatives, you get negative coefficient. Complex exponentials, when you take two derivatives, I squared is minus 1, or minus I squared is also minus 1. So these solutions no longer work. I have to come up with a solution that will now work. So what kind of solution, just taking a guess, would fit to be a solution to this differential equation? Exponential, right? Real exponential, not complex exponential. So that's what it's going to be. Normally people use kappa for, yeah, I think I can keep using kappa. So instead of the complex exponential I had before, it's going to be real exponential. C times e to the, oh, sorry, almost wrote I. Kappa 2. Sorry, my kappas and k's often look the same. So I'm going to call it kappa, but if it looks like a k, my apologies. But 1 and 2 distinguish them, so I think it's not going to be too confusing. So this is one solution. There's another linearly independent solution. That's this one. E to the minus kappa 2x. Because when you take two derivatives, it doesn't matter if this was minus or plus. So this is my new solution in the region 2, beyond the step. And all right, so those are my, oh, I guess I should write down my definition of kappa. So kappa 2 is defined as square root of 2m v naught minus e over h bar. And just to make sure we didn't make any mistake, is my kappa 2 real and positive? As in, the thing that I'm putting under the square root, it's positive. Right? Good. All right. So, okay. So I have two general solutions. 1, 2, 3, 4 free parameters. I'm going to get rid of one of them, a, by setting it equal to 1. All right. I still have 3. So I can write down two equations by applying boundary conditions like last time. So let's just start out with that. So my first equation is the continuity of this wave function. So it's going to be, so a times 1 plus b times 1 again is equal to c times 1 still? Yeah, okay, it's still 1. C plus d. Let me replace a with 1 because that's what we are going to do in the end anyway. All right, I guess that's good. Continuity of the first derivative, the wave function must be smooth. So imagine taking the derivative here. I get factor of ik minus ik1. So it's the same thing we did last time. So setting a equal to 1, I get ik1 minus ik1b is equal to, now this time I just get kappa 2 and minus kappa 2, no i's. So I have kappa 2c minus kappa 2 kappa 2d. All right, two equations, 3 unknowns. I need to reduce this down to only 2 unknowns. So you know which coefficient I'm going to try to get rid of, right? Any ideas? Which one do you think I'll try to get rid of? D? I think the way I wrote it, it's actually not D. So here's the thing. When we had a complex exponential solution, there was a very clear physical meaning to them. That it's a traveling wave with some particular momentum. When you have a real exponential solution, can you still say that? No, it's no longer a momentum eigenstate. So I'm going to get rid of one of these two. I just need to come up with a different excuse for getting rid of it. Why C?
Because it's not going to increase.
Yeah. So when you look at C, so you know these wave functions, they start at the barrier x equals 0. That's where they start. When you look at the term that goes with the C, it looks like an exponential increase. When you look at the term going with the D, it looks like an exponential decrease. So whichever wave function it is, you don't want it to blow up to infinity because you cannot normalize something that blows up to infinity. So this is behaving okay. It's exponentially decaying. This is not. So the only way to make sure my overall solution comes out right is by saying, all right, for whatever reason, this C is going to be 0. I guess the normalizing the wave function makes it 0. Yeah. So yeah, so I get rid of C. So this is the only term remaining. Now I have something I can solve for. So let me just solve for B, since we don't have that much time, and I guess even if we were to find the coefficient D, I'm not entirely sure what meaning I can assign to coefficient D. So, so let me just solve for B, because B can still work as reflectivity, or I guess the technical names are, when I get B, the name for this is the reflection coefficient. And when I calculate B, absolute value squared, this will be reflectance. And I was trying to look up the difference between reflectance and reflectivity. You can correct me if, look it up on your own and correct me, send me a message if I'm wrong. I think it's the same thing. I think both means the same thing. Maybe, maybe not. But I'm looking at how much intensity gets reflected. So, all right, let's solve for, so I have to get rid of this C here also. So get rid of this C. So let's eliminate the solve for B. So, I guess I already have this solved for D. So I'm just going to plug this in for here. And when I do that, I end up with I guess I cannot get rid of this I anymore, right? I have it. I don't have I everywhere, so I cannot cancel it out. So it'll be IK1 minus IK1B is equal to minus K2. Kappa 2. See, I'm confusing myself. Times 1 plus B. All right, that seems like a simple enough algebra, but maybe not that simple. Okay, I'll move B over, move kappa over. Then when you do that, this is what you end up with. IK1 plus kappa 2 is equal to, having moved the B over, I have plus IK1B minus kappa 2B. Everyone good? So when I factor out B, I get, so this is the thing inside, minus IK1 minus kappa 2. So when I solve for B, this is what I end up with for B. B is equal to IK1 plus kappa 2 over IK1 minus kappa 2. Okay. I get a complex coefficient, and there's really no getting around that. Yeah, well, there's no getting around the complex coefficient in this case. Okay. And so I guess I can give you this general rule. In quantum mechanics, as a rule, you have to deal with the complex functions. The only circumstance where you can avoid doing that are bound states, like infinite square well. When you have a bound state, then you can kind of choose to deal with the real functions. But any other, so this is not a bound state, right? You have a traveling incoming wave that gets reflected, gets decaying. It's not a bound state. And in that case, well, in general, you cannot avoid dealing with complex function. So, all right, so we have this value of B. What does your intuition say, the condition, what kind of condition should this B obey? From your, I don't know, classical intuition or your physical intuition. Like for this situation where you have an incoming particle of energy less than the barrier, how many of these particles should reflect? All of it, right? So right now you might be a little bit confused looking at B and seeing that it's not equal to 1, right? This is where it's important for you to remember that the wave function itself, quote-unquote amplitude, it doesn't mean anything. It has some phase factor in it, and phase factor doesn't have any physical meaning. other than phase difference. So really, you have to take the absolute value squared. And it's important that you remember that this absolute value squared actually stands for this mathematical operation, complex conjugate times the wave function. So when I take the b absolute value squared, let's hope that we get 1, because if it doesn't, then I made a mistake somewhere. So let's try it out and see. So let me do this calculation here. B absolute value squared is going to be complex conjugate of this, which is minus I k1 plus kappa 2 divided by minus I k1 minus kappa 2. That's complex conjugate times the B itself. So I k1 plus kappa 2 divided by I k1 minus kappa 2. I see some cancellation. That's hopeful. So all this really is minus times this, right? So this cancels out this, except you leave a minus sign behind. Let's hope it gets canceled out somewhere else. Oh, I think these two are opposite of each other, meaning I can rewrite this as a minus this. Wait, that's not right. Wait, let me rewrite it correctly. I can rewrite this as factoring out a minus. I can have a minus sign here. So minus here and then plus here. Yeah? Then this cancels this out exactly, having left a minus sign. These two minus signs cancel. So I do end up with a 1. The reflectivity is equal to 1 here. Particles coming in have 100% chance of reflecting. So let me ask you this question. So the fact that particles coming in having 100% chance of reflecting, is there any probability, any chance for the particle to be found within this barrier region? Like, what would you say is the probability of detecting particle? Would you say that this is equal to 0 in this region here? So this is the curious quantum mechanical fact. The value of D, whenever you find it, it's not going to be 0. And this value of D will determine where it's starting from. And it's an exponential decay. It's not an immediate decay. It does decay with some particular characteristic length, which means the value of psi of x here, it's not 0. Which means when you take the psi absolute value squared, that's going to be bigger than 0. Which means you have non-zero probability of detecting particle in this region. And I guess intuitively, this is how it connects to the quantum tunneling, which you are going to work through in a homework problem or something, is if this barrier was so narrow that if the barrier ended before this wave function entirely decayed, that's where it would tunnel through and continue to go through. And if that's the case, that will modify the coefficients. When you apply the boundary conditions, B will change ever so subtly so that it's no longer equal to 1. So I'm not actually showing that. And here's the second thing that actually took me a long time to be reconciled with, that it's actually a physically true thing happening. Suppose you ran your particle detector or whatever, and you actually found the particle to be located here. You actually found the particle here. And you know particle came in with some amount of energy E. How much energy do you think this particle would have here if you found it at this X location? Do you think the particle here would have energy E or some different value? No, some different. It cannot have energy E because at a minimum, it needs to have the potential energy. So if you found the particle here, the moment you detected it, its energy was at least V naught. And it probably was moving too. In that case, it might have an even greater energy than V naught. So what's happening here? I thought the particle only came in with the energy E. Like how did it end up with more than the energy it had at the beginning? So, this is something that when you feel like you understand this is when you are beginning to understand quantum mechanics. I'll just tell you my process, kind of describe the process I went through, and it'll take you some time to actually think this through. It usually takes upper division quantum mechanics. So what I thought was then, does this mean energy conservation is violated? It absolutely does not mean that. I can tell you right now that nowhere in modern physics, energy conservation is ever violated. Nowhere in quantum electrodynamics, nowhere in particle physics, energy conservation is ever violated. Now, you can write your equations in a way that looks like energy is violated. Those are bad ways of writing your equations. You write it in a Lorentz invariant way that says energy conservation is absolutely observed. So energy conservation is still observed. So how is it observed here? So for you to be detecting particle here, it must be interacting with something. In fact, that's how you're detecting the particle. If this is an electron, it could be you are shining light. And that light would consist of photons. For you to localize the particle at this location, the photon will have to be particular wavelength, and that wavelength of photon will have enough energy to impart to the electron to actually, say that, all right, to give enough energy to it. Once it's detected, it does have more than the potential energy, and probably quite a bit more because you're localizing the particle. But so all of this, like, you didn't hear experimental description of that when I was working it out with these differential equations. Is that all these things are built into our theory. Into our theory, we are building in that whatever detection you do, it's going to interact with the system and disturb the system. And that's a kind of intuitive origin of the uncertainty principle. That when you try to localize the position, in the process of it, you're just going to impart some amount of momentum to increase the momentum uncertainty. And so here, energy conservation is still fine. The moment you detect the particle here, whatever detector you're using have interacted with the particle, gave it enough energy so that it's okay to be here because now it has more than the potential energy.
So say so theoretically, like conceptually, just theoretically, like if you don't ever detect it, then the particle will never be there then?
So that's a very good question that you will only get a satisfactory answer to in maybe upper division quantum mechanics. So you are asking me where was the particle before you detected it, right? I refuse to answer that question because whatever answer I give is not going to be correct. So this is the standard answer. The Copenhagen interpretation of quantum mechanics, which is the standard version taught in upper division, is that before you detected it, particle didn't have a position. It's an unsatisfactory answer, but that's the mainline, mainstream interpretation that I'm required to teach you. So, all right, so that's all the solution with the step function.
So what I like to say about physical intuition is when you know the answer without having to do detailed calculations, and mathematically complicated situations like what you will see this week is where intuition really helps, because the kind of sense of understanding is different when you have to work through difficult calculus and algebra without feeling like you understood anything. Then you might be able to do the algebra and calculus and won't feel like you understood anything. That's one sense of feeling. And
The other is where you kind of know what the answer will be based on your intuition. And the purpose of calculation is to verify the answer that you already could have guessed. And when you're in the second scenario, that the kind of the sense of what you feel like you understand is quite different. So I hope so the purpose of all this is to help you build your intuition so that as you're going through those technically challenging calculations that you feel like you know the lay of the land better. So let's see here. Let me just launch this simulation that we are looking at last Friday, to see if there's anything here that we didn't quite go over that maybe we should. Possible by bits and pieces that we already did everything. So I think there was really one thing that I wanted to demonstrate. So last Monday I showed a little bit of what quantum tunneling looks like. So just to quickly show, the setup for quantum tunneling was you have some energy, or you have some barrier of some amount of energy, and you have incident particle of some energy, and with a precise enough definition of energy. Note how I have to make the wave packet broader in position in order to define its momentum precisely enough so that its energy is definitely below the barrier height. That quantum tunneling describes the phenomenon where there is a non-0% chance of the particle being found in what's called classically forbidden region. So there's a little bump here. So when I make a quantum measurement, the likely chance is okay, it's gonna be here. And I think in order to actually in order for me to have a reasonable, so I'm gonna have to make this measurement like 1,000 times before once there's a particle on this side. So I mean, let me just try 2 more times in case I hit the lottery, but I'm probably not gonna do this in a live session. I'm not gonna rely on me getting one measurement on the right side. Okay, let me just do it one more time, just in case I hit the lottery. And I might actually do this on a recorded video. On a recorded video, I can kind of count the number of trials and see how many trials it takes before here, so you see a particle being found within the barrier. That is already something. So anyway, so I'm not gonna actually do this measurement until I find the particle on the right-hand side. But 1 in 1,000 chance is actually not that bad, or 1 in 1,000 or 1 in 10,000. Compared to the classical prediction, which would say you would never find this particle on this side. So we talked about the tunneling last Monday, and tunneling is one of the wave mechanical phenomena that you wouldn't expect or predict based on classical mechanics. We call the region beyond this first rising part of the barrier classically forbidden region, because classical mechanics would predict that the particle is never found on this side. So that's one. I wanted to show you one other phenomenon that you wouldn't quite expect classically. So let me set that up. I think my wave packet is okay as it is. I don't need to change anything there. Let me change the barrier this way. So I can change the barrier so that I guess I can do this multiple different ways. Let me do the simplest possible scenario, which would be where instead of there being a barrier, there is a drop in potential. So potential goes from 0 eV to minus 0.5 eV. And let me just leave it staying at the lower the potential. Now, if someone were to ask, what would the classical mechanics predict? This is like, imagine a ball well, it's not really the best example because there are places where you can poke holes in it. But imagine a ball kind of rolling along. It has some kinetic energy, and then it's suddenly going over a cliff. And classically, you would say, oh, the ball's gonna just keep on rolling, or it's gonna keep on going, except here, because of a bigger difference between the total energy of the particle and the potential, there will be greater kinetic energy. So the ball will go faster here, but from left to right, if the ball comes in from left, it'll just keep on moving to the right. Now, quantum mechanically, let's see what happens. Okay, so for the most part, it's right. The ball continues to move to the right. And if you carefully measure this wavelength and compare it to the wavelength before, you will find that, yeah, wavelength did get shorter, meaning increase the momentum. But here's the result that you might not have guessed based on classical intuition or classical prediction. There's a probability that particle will bounce back. Some people like to joke it as like quantum mechanics predicts that if you drive a car over a cliff, that there's a chance that your car will bounce right back from the cliff. Of course, that's not to be taken seriously. If you actually work out the real probability of macroscopic event happening like that, it takes many lifetimes of universe for something like that to actually happen. But as an analogy, it's not wrong. As in, so you can imagine setting up this experiment with an actual electron, and you can set up this experiment with electric fields. So in a setup like this, in most of the regions, your electric field would be zero. That's what this flat potential represents. And where you have this sharp potential drop, you would have a large electric field, not in the direction that opposes the motion of the electron, but in the direction that actually helps the motion of the electron along in the same direction. And experimentally, what you would find is that there's some probability that the electron actually bounces back from that drop in potential that should actually help him move faster. And trying to think of this like a particle motion, it makes no sense. But if you think of this like a motion of a wave, this actually makes a perfect sense. In fact, you have an you have seen example of this, even though we didn't go through it in detail. You have seen in the optical phenomena, you've seen the refraction and reflection. And light, when it goes from one transparent medium to another transparent medium, and index of refraction changes abruptly, the light bounces from that. It has a chance of bouncing from that boundary. And that is what you are seeing here. In fact, a big chunk of this phenomena really closely resembles what you see with the light going from, say, vacuum, index of refraction of 1, to a region where the index of refraction is greater than 1. In this sense, when light goes from region with small index of refraction to large index of refraction, the wavelength gets shorter. You can work through the algebraic relationship to see. And here with electrons, that is what you are seeing. It has wavelength of about 1.5 divisions before it enters the other side of the potential. And after it enters the other side of the potential, the wavelength on the other side becomes 1 division. So wavelength got shorter by a factor of like 50 or not quite, well, work out the ratio however you want, either 33% or 50%. So wavelength got shorter. So the medium here represents medium where the index of refraction is larger. And so, with the light waves, you have seen that, and we didn't bat an eye at light waves or photons bouncing from a place where it had a longer wavelength to where it had a shorter wavelength. And really what causes the reflection is this sudden change of potential energy. So I guess the intuition that that I hope you are beginning to build is the intuition or is the habit of thinking of everything as waves. So the kind of thing I was pointing out, it only sounds paradoxical and difficult to understand when you try to continue to insist on electron as particles. And I think one of the first things to learn in quantum mechanics is learn that everything has wave nature. It's a question of under what conditions you see those wave natures manifestly. And in case of electrons, it takes these kind of microscopic scales. Let me just show you one more. So something like this, it's not something that would have any final effect on motion of a classical particle. But when you let this quantum mechanical wave go through, this is what you see. And I think it's going to look quite complicated. So it's so you have two boundaries, so you have reflections happening on two boundaries. There's a reflection from here, there's a reflection from here. So I think within this region, well, both the first and the second region are just going to look complicated because the representation of the wave in these regions are going to be superposition of the incident wave and reflected wave, incident wave and reflected wave. And then I don't know if this simulation actually simulates multiple reflections between these two boundaries. At some point, it becomes not quite significant. And I think your textbook actually might even have a formula to work this through. Let me just double check if it does. I know your textbook has a formula for quantum tunneling. And if you look at this carefully, it's actually not all that different from quantum tunneling. In case of quantum tunneling, your potential looks like this. And in the scenario that I just ran, everything is the same. The only thing that changes the potential height. It goes from something positive to something negative. And depending on how your textbook derived it, the formula your textbook derives might actually be applicable to when the potential barrier is negative. Let me just look to see. I'm curious. So, this is the situation it's describing. Let me just skim through the derivation that they're doing. Yeah. Oh, okay. I don't think you can just take the formula and apply it here. Yeah. It's something that you will note in some of your homework questions and in lecture. And it has to do with the fact that the form of the solution in this region, it really depends on what the difference between the potential and the energy is. Because when the difference between the potential and energy is negative, then the solution that fits in this region is not the oscillating sinusoidal solution, but as they will, wait, today not right? Yeah, as you'll drive in region 2, it's gonna be a real exponential solution. So, so yeah, you can't just, because that's an actual big thing that you have to make a decision on. So if you were to simply take this complicated formula and try to apply it here, it won't work. Or I wouldn't expect it to work. There could be some crazy coincidence where it does end up working, but at a first glance, I wouldn't expect it to work because this scenario and this scenario are qualitatively different in what form of a solution satisfies the Schrödinger equation in that region. So, so yeah, but it's an interesting question. You can actually work out, if we have a potential dip instead of potential barrier, what are the transmission probabilities and reflection probabilities? And the thing that's really quantum mechanical or wave mechanical at least is that transmission probability in this case will not be zero. Except at some particular widths where you have resonance transmission. But let's not get into that. So this simulation is a lot of fun. There's a lot of things you can do that I won't do now, and you can go through this if you want. What I want you to try out was something that I've never done in the past semesters, mainly because I figured this is gonna get mathematically super complicated. I don't want to work through it, and even if I wanted to, it'll take a super large amount of time, so I haven't done it. That's what this is, dealing with the tunneling things. Now, your textbook does handle tunneling probability. So, it's not like if I didn't cover it, you would miss out on it or something. So, about, 15 pages of stuff to get to this formula. And I think they actually skipped quite a few steps. So what I want you to give it a try of is working through this picture just on SageMath. And I think I can maybe even possibly do this without writing down anything. So I wanted to give that a try. I haven't done it yet, and maybe I should have practiced before this meeting, but I haven't. Let's see what happens. So I do think there are some things I need to write down. So let me do it this way. I'm going to write down the time-independent Schrödinger equation, because that's what we are solving through here. So this is the potential that we'll be dealing with. And I'm going to just type in some of the information that is in the textbook. So some of that information is things like the time-independent Schrödinger equation. So this is the time-independent Schrödinger equation. And we need to write this equation in a couple different regions. Regions 1, 2, and 3. So yeah, let me maybe start out with that. I'm going to first define some of the variables I'll be using. Declare them h bar and psi, maybe x. Think not this as a function, but I'll be using u naught to indicate the barrier height. And I need E for the energy of the particle. So with those, I can define, let me declare a function. So psi is a function psi of x. I think that's the right way to declare it. So my first differential equation in region 1. So that's going to be my thing here, minus h bar squared over 2m times the second derivative of psi with respect to x twice. Sorry, there's a better syntax, but I don't remember it at the moment. And this potential portion, it becomes 0 because in this region, the potential energy is 0. So that left-hand side is equal to the right-hand side. Energy times psi of x. Just psi. Let me see if this looks right. Yeah, that looks about right. Yeah, so that's a differential equation in region 1. Differential equation in region 2 looks very similar. So let me start out with this and then insert the parts I need to. So I have this potential energy term. It's going to be u naught times psi, and then the rest is the same. And my differential equation in the third region, that's going to be the same because it comes back to the same potential. So I'll just remember that. So when you have these, I think you should be able to solve these equations because once you have this time-independent Schrödinger equation, this is what's known as ordinary differential equation. It doesn't involve partial derivatives. So there are mathematical methods that'll just allow you to solve for it. So I should be able to, I think there's a function called a dsolve, or differential equation solve. Oops, sorry. I meant to say help. That's all. So hopefully that'll give me some syntax guide. Yeah, differential equation solve, differential equation, a dependent variable that be psi. Initial conditions, I'll start by not putting anything in, and the independent variable should be x. Okay, I think I have enough. So solution in region 1, or solutions in region 1 should be solve this differential equation for the differential equation 1, and we are going solving for psi, no initial conditions, and my independent variable is x. So it's asking for some of the assumptions. For example, is energy times mass positive, negative? Yeah, that's going to be positive. So let's say assume E times M is greater than 0. That's the syntax. So this is one of the failings of computer algebra system, which is that they tend to treat all the quantities as super general. It's treating E and M as if they could be complex coefficients. I know they are positive, so I'm telling computer algebra system to assume this product is positive. So let's try it again. I thought I already did that. All right, let me just make it a little bit easier. Let's have it assume that energy is positive, and have it assume mass is positive. They're both positive numbers. Okay, you finally have an answer. So when you look at this general solution, you see that it has, that could be troublesome. Maybe it won't work. So it's using these as the solution thingy, and yeah, maybe so in region 1 that's not a problem. You can kind of see it here with the region 1. So when it solves for the region 1, they don't eliminate anything, they just keep everything. And I can do as far as so assume U naught is greater than E and solves 2. I can do the solution for differential equation 2 psi whatever is x. And once you account for that, the fact that this is greater than that, so this is square root of this thing, that's just gonna give you it's gonna give you an imaginary I. So this product here will end up giving you a real argument here. Then that kind of matches what they have here. Maybe let me give this a try. So instead of having these different differential equations, I can actually just keep this one, and whenever I want to go back to differential equation 1, it will be really plugging in that U naught is 0. So yeah, I think I might be able to do that. So let me do it this way. Solution in region 1 is going to be, instead of that, I'm going to use a differential equation solve dq2 psi I bar equal to x. And what I need to do is substitute in U naught is equal to 0. To the solution, just to substitute in U naught equal to 0. All right, I think that's exactly what I wanted. So I prefer this complex exponential form. So for in region 1, it actually doesn't make any difference. You just, the choice of whether you use trig functions or complex exponentials, all it'll change is how do you express these coefficients, and they will end up working out fine. But the problem will be in the region 3. So I have a solution in region 1, I have a solution in region 2, and I need a solution in region 3. And one of the things that you will see them do when they work out the solution in region 3 is they will get this answer. So solution in region 3. So in this answer, what they do is they set G equal to 0. This is on the justification that each of these they stand for a momentum eigenstate. This portion stands for a wave that's traveling to the right, positive momentum, and this stands for the wave that's traveling to the left, negative momentum. And in order to make this solvable, what they do is they specify an initial condition that the wave is coming from left to right. So in this region, there's incident and reflected waves. You have waves going in both directions. But once you are through the barrier, you only have transmitted waves. So with the solution 3, so I can get solution 3 the exact same way I got solution 1. So I'll start from here. Now, what I need to do is I need to make this portion of the solution go away so that I don't have a wave in this region that's traveling to the left. So solution 3 is equal to solution 3, substitute in K2 equal to 0. Right? Yeah, okay. Yeah. All right. So I have solutions 1, 2, and 3. I think it's let me assign some symbols. I'll use the same symbols that the textbook is using. So it'll be variables A, B, C, D, and E, I think. Right? Oh, they skipped E. So let me use F because E stands for energy. So okay. So my solution 1 will have coefficients A and B. So let me just substitute those in. I'm doing this mainly so that this underscore K1 in different contexts don't get mixed up. So underscore K1 is equal to A, underscore K2 is equal to B for solution 1. So for solution 2, underscore K1 is equal to C, and underscore K2 is equal to D. For solution 3, no, not yet. Solution substitute in underscore K1, the only remaining parameter, that's equal to F. Okay. So I need to write out some of my boundary conditions. So I have this, what your textbook describes as here. You have boundary conditions setting that the derivatives are continuous at the boundary and the wave functions are continuous at the boundary. So my equation 1, which I haven't defined yet, should be okay. Let's say my wave function is continuous at the boundary. So I say solution 1, substitute in x equal to 0 is equal to solution 2, substitute in x equal to 0. Yeah, that's my first boundary condition, equation 2. And that will be this equation here. The wave function is continuous at the right end of the barrier. Solution 2, substitute in x equals L is equal to solution 3, substitute in x equals L. Oh, I need to declare L. Okay, so far so good. That looks complicated. Let's keep going. So I need the third equation, which is the continuity of the derivative of the wave function, that it's a smooth. There's no kink, a sudden change in slope. So I need to say derivative of solution 1 with respect to x, and substitute in x equals, so it's a boundary at x equals 0. So that value should be equal to the derivative of solution 2. Let's keep going. Equation 4 is the continuity of the wave function on the right side of the boundary. So derivative with respect to solution 2, derivative of solution 2 with respect to x at x equals L is equal to derivative of solution 3 equation 4. All right, that looks good. So I have a system of 4 equations, and equations 1, 2, 3, and 4. And all the parameters like E and M, they are, or U naught, or L, all those are known quantities. So I can imagine doing something like, let me say my rule is, so my incident energy, let's say that that's 1. And barrier height, I'm gonna make it higher. Let's say that's 3. And my h bar, I'm just gonna set it equal to 1. I'm choosing some natural unit system. And my L, once I've chosen this natural unit system by specifying h bar and m, there should be some constraint on L. I'll just say L is equal to, I don't know, 0.1 for now. So when I substitute in these parameters, then each of these equations, take some equations of these unknown quantities, coefficients, C, D, F, and C, equation 3, yeah, A, B, C, D. So I have these unknowns, and I have 5 unknowns, A, B, C, D, and F. So in order to make it tractable, because 5 unknowns, 4 equations, you can't solve it. The computer algebra system won't know what to do with it. I can say, okay, we'll say A is equal to 1. So we are normalizing it with respect to incident wave. So I'm gonna say equation 1, that's gonna be equation 1 with A substituted in for 1. And same thing for equations 2, 3, and 4. Now, when I have these equations, they should now be equations in terms of 4 unknowns. So this is what I can do. I can get a solution. I haven't used the solve yet, right? Okay. So solutions. Yeah, solutions. I'm going to solve this system of equations 1, 2, 3, and 4 for the parameters A, B, C, D, and F. Wait, not A, B, C, D, and F. Okay, I think that should do it. So it's something, and I'm pretty sure, yeah. Wait, let me look at the length of the solution. Yeah, there's only one. So my solutions really should be, and this should now be a length of 4, I think, yeah, because it's giving me values of B, C, D, and F. And I can make an argument that the only parameters that I really care about are B and F. because B is going to be associated with the reflection probability, and F will be associated with the transmission probability. In fact, let me do this. Solution. So this will give me B. Let me substitute in the rule that I had above. So I get this. Yeah. So here, I guess that itself is a rule. So I think I can do this. Absolute value of B squared, where I use this as my substitution rule. No. Or get this, and then take the right hand side, and then I think I can take that absolute value squared. What am I missing? Oh, I think I know why. So, numerical or decimal approximation. Okay, good. So this is the coefficient B absolute value squared. Let me try something similar for the last solution, which is our F, and I'm going to do the same thing. Take the right hand side, put it through the decimal approximation, and say absolute value squared. And here's the fun thing. Watch this and this. They add up to 1, which is what you would expect. If you have a wave that's incident and some tunnels through, then you add up what tunneled through, add up what reflected. They should add up to 1, because everything that's incident either tunnels through or it gets reflected. And we can do other fun things. Here's one reason I defined the rule as a dictionary. We can basically see how this tunneling probability changes as I change the thickness of the thing. So at the moment, I think this is a probably pretty thin barrier, which is why most of it is reflecting. I can update my rule to say, okay, my L, let's make it 10 times as thick. Oops, is that not how? Oh, wait, I need to put in a dictionary. I'm forgetting my Python syntax. Okay, that's my new rule. And let's see what happens now. So let me see here. I'm gonna try to build this into. So I have this. Let's see, put it through n, and then absolute value squared. This is my b, and my f is gonna be this thing here. Yeah, now it's kind of flipped around. It's more likely to reflect than to get transmitted through. And there's a lot of fun things you can do with this. I guess I'm over time. Let me do just one thing. I think, let's see, redefine a rule without the L so that I can do this. I can define a range of L values. I think I can use linspace. All right. I'm gonna just import numpy. Linspace is what I remember, I think. L, so numpy dot linspace 0 to 0.01 to I don't know 1. So I can do 100. Okay, something like that. All right. So I can define this as my values of L's, and given that, I think so. This thing that I was calculating. So I can do something like this. Substitute rule, and then substitute again. This time I'll say L is equal to L's the 0th parameter, for example. Yeah, something like that. That works. So what I can do is I can build up the values. So for example, reflection probabilities is equal to this thing here with some judicious edits. Substitute here. L is equal to L value, and I'm going to build the remainder of the Python syntax for L value in else. L val that's a kind of dummy variable. It doesn't. So this is all the reflection probability values. Let me do the exact same thing, except it's not transmission probability using the F values. And I think the rest will work out fine. So these are reflection probability values and transmission probability values. And I want you to just plot these. I want to see if I can just plot them as a function of L values, and because when you're using, at some point when you're using computer algebra system, doesn't really simplify expressions that you want it to. So at some point it becomes necessary to just do a numerical representation, graph it out to see if that gives you some sense. Oh, maybe I could have done something different. I think instead of that, sorry, I'm kind of doing this on the fly. So in this expression, so the reflection probability, I had this. I don't really need n, and I think I can just go with not plugging in L. I have absolute value squared. I think that might actually give me an expression that I can plot. Let me give this a try. Plot this for L 0.0121. I don't know. Maybe. Let me see if what happens if I plot this for a greater value of L. So anyways, let me just stop it here. I'm already 12 minutes over, but it's a kind of exploration that can be fun. That, this kind of, when you look at the derivation that's in the textbook, like my eyes glaze over just looking at it, like just trying to make sense of this. But kind of solving through computer algebra system and plotting it out numerically and making sense of that. That's the kind of thing that that's more tractable. It's kind of easier to play with than this complicated expression here. So anyways, I just wanted to try that out, demonstrate some of that. Stop the recording here, and see you all tomorrow.